So I just want to motivate why we want to build spectrometers. So every atom and every molecule emits radiation at radio wavelengths, and nature's kindly made every molecule radiate at a different frequency. And I'm particularly interested in whether there's life out there, are we alone? And so some of this stuff is very useful. These are some of these early building blocks of life, amino acids and the things that you and I are made of are out in space, and you can discover that by building a spectrometer and figuring out which molecule is which and how much it is. You can also not just figure out which molecules and which atoms are out there, but if you have good resolution, you can look at the line profile. It measures the abundance. You get the temperature by the width of this line. You can get the velocity by the shift of the line. You can map out the galaxy and the structure of the galaxy, figure out which way the spiral arms are moving around. You can measure the expansion rate of the universe from measuring the velocities of galaxies. There's all kinds of things you can do if you have a spectrometer. If you have a fast readout spectrometer, that means you get a spectrum every millisecond or something like that. Then you can look at time variable things like pulsars and fast radio bursts. So this is from a FRB or a pulsar. This is one spectrum. This is maybe a spectrum. Oh, I'm sorry, I got this backwards. But so you get a bunch of spectra that happen every millisecond, and then what you find is that there's a dispersion. The low frequencies arrive later than the high frequencies. And that happens as the radio waves travel through the plasma and the interstellar medium. And then you can use that not just to find pulsars, but you can measure the amount of gunk between you and the pulsar or the fast radio burst, and that tells you something about, you can weigh the universe. You can measure the baryon density of the universe this way. So there's a lot of really good stuff you can do with spectrometers. This is the first fast radio burst. We still don't know what causes these things. Amazingly bright objects that you can see it almost to the edge of the galaxy, very high redshifts. We don't know how you get that much energy. They're the brightest thing in the sky. They last about a millisecond. So I want to say a little bit about how you build spectrometers. At optical wavelengths, I think all of you are familiar with spectrometers made out of prisms or diffraction gratings. That doesn't work well at radio wavelengths. The early spectrometers were these things, what I call scanning spectrometers, where they would move from frequency to frequency to frequency, one frequency at a time, like a police scanner. Also, if you've got a spectrum analyzer in your lab, that's the way it works. It sweeps across, measuring the power one frequency at a time. The problem with that is it's very slow, so telescope time is expensive, a few $1,000s an hour. So what you'd like to do is, instead of scanning across the band, you'd like to have a filter bank, and we just heard about filter banks from Jim, where you it's essentially a bunch of radios, each one tuned to a different frequency, all working simultaneously. You can think of it as multiple receivers, multiple radios, or a filter bank like Jim was talking about, or you can do this with Fourier transform. The early multi-channel spectrometers were made with analog filters. The new spectrometers that are the CASPER spectrometers, and most everybody uses these digital filters, which you can build out of a Fourier transform. Deepti talked about how to do that. Where you digitize the time domain data with an analog digital converter. You get a voltage as a function of time, and then you can compute the spectrum either with a Fourier transform or a polyphase filter bank, or different ways that you can compute the spectrum. So the typical kind of architecture is you digitize the data coming from your receiver on the radio telescope, and then you put that time domain data, this voltage as a function of time, into some kind of computing thing, a CPU or a GPU or an FPGA, depending on how fast the samples are coming at you. I think I mentioned earlier that this thing can handle about 50 megasamples per second. This thing can handle about a gigasample. This is tens of gigasamples. But as you go this way, it gets harder and harder to program, and that's what CASPER is trying to work on, is how can we program these things easily, or even these things. A lot of people can program these things in C or whatever your favorite language is. CASPER is trying to make it easy to program these things so you can handle high data rates or many antennas. That's what CASPER is about. And we use these languages that make it easy, so that it used to be if you wanted to program an FPGA, You had to be a super expert, very obscure languages, and you had to be really good at engineering and computer science. But CASPER's trying to make it easier to program these things. Even if you don't know how to program these things, I think there's just a lot of libraries and tools that you can just download without knowing the guts of them. Jim talked a lot about the polyphase filter bank. This is, I think you showed 3 of these channels, Jim. This is just showing just more of these things. That's what you want to build in a spectrometer. These are these brick wall filters that make a really good spectrometer, where you, if the signal, if you have a strong signal here, it doesn't contaminate the neighboring channels. You don't have to build a polyphase filter bank, Jim pointed out. You can just do a fast Fourier transform. It's not as good. You don't get these brick wall sharp filters, but in many, that can be good enough.
So I'm feeling a need just to ask, maybe you could do this, to ask for an explanation at even a more basic level of what we're looking at there, this thing called the spectrum. That you start with this ABC taking a series of samples in the time domain,
yeah,
be they real or imaginary, and this machine called a spectrometer that you've built, and they're genuinely useful machines, basically decomposes that time series into the frequencies that
right.
constitute it.
So that's this diagram here. Let's ignore this for a second. But so this is what Jonathan's talking about. Is I haven't shown here, but there's a telescope here. There's some receivers and stuff. You get this voltage as a function of time coming out of your receiver. Then we turn that voltage as a function of time into a bunch of digital numbers, a sequence now of digital numbers, which are voltage as a function of time, discrete data. And then a typical thing you do is to do this Fourier transform, which is what Deepti was talking about, where you try to fit sine waves to your data. You try to fit all these different sine waves. And you're measuring how well each one fits, and that gives you that spectrum. What Deepti was talking about was fitting sine waves and cosine waves, because we don't know the phase. And then this detect thing, because the fitting, it can go negative or positive, the detection is squaring the data, so you get just positive signals. We're measuring the power voltage squared. Is that what your question is?
I think so, but just actually also just go back to the PFB picture.
Yeah.
And what you're seeing there really is the response, not
right.
what you're measuring. It's what the instrument puts a filter over the time domain signal, and the x-axis or the abscissa is frequency, and you're measuring how much power there is at every frequency by putting a little filter over the
right.
series, right? So this
each one of these things is a filter.
That's right.
And if you just pick out a particular color here, let's pick out this particular channel. That's one channel of your filter bank. And what this is trying to show you is that if the frequency that you're looking at is here, you get good sensitivity. And if it's here, it's much reduced sensitivity. So it's only sensitive to a certain range of frequencies. That's what you want in a filter bank.
Yeah, but and each of these bins would only fill up to the extent that there's power in that band. Right, I mean, this is the response of the instrument,
right.
Not the spectrum of the signal.
A perfect filter bank would be what we call a brick wall filter, infinitely steep and flat on the top. That's kind of impossible. It kind of violates Heisenberg, but yeah. So, but this comes really close. Okay, so in this spectrometer, by the way, this FIR thing that I didn't mention before, that's an optional thing. That's the thing that Jim was talking about, to add the polyphase to make really sharp filters. You can add that in, and as Jim pointed out, it doesn't take much extra computing resources, and if you want those sharp walls and flat response, you should add that thing called the FIR, part of the polyphase. It makes it into a polyphase spectrometer. But that's an optional thing if you think you need it. The detector is important. That's the thing that squares the voltage, so you're measuring power. And then this thing is to integrate the data. You take a sum of a bunch of these samples, and you build it up, and you get beat the signal to noise by adding up a bunch of spectra together. So that's a simple spectrometer.
There's nothing intermediate?
Well, this is... This is another way to build a spectrometer this is one implementation of a spectrometer. You digitize the data, then you might break it up into channels in this FPGA board called a Roach board, which I think Jack will talk about it, but some FPGA board that breaks it up into channels with a polyphase filter bank. And then you might squirt the data into a switch, and then on the back end you might have some computers, maybe some GPUs that do more processing. This thing is how to build a spectrometer inside an FPGA. So CASPER uses this language called simulink, which is a graphical language. It's kind of like a flowchart language. And you don't have to understand all these blocks. But there is a tutorial on this thing if you want to learn how to program these things. One of the tutorials you can do in the afternoon on Wednesday, Thursday, or Friday is the spectrometer tutorial, where you learn what all this stuff is and you learn how to compile it and how to build a spectrometer. And but what's happening here is this is the ADC block, the analog digital converter, and then this is the FFT block. In this case, I believe there are two of them because this is a dual polarization spectrometer. It's digitizing two channels. And then these are accumulators that do the integration. There must be detectors. Oh yeah, here's these things called power blocks that do the detection. And then these are the accumulators, the vector accumulators. And then these are things to get the data out over the Ethernet to your computer. And there's a lot of little stuff here that you don't have to understand at all, but that's kind of how you program these FPGAs. I want to also not just talk about spectrometers, but I want to talk about these things that CASPER, a lot of people build, are these things called beamformers and correlators. These are to make images on the sky. So a spectrometer, you look at a single pixel on the sky, but if you have a beamformer or correlator, you can look at lots of different places on the sky. And typically what astronomers want to do is build something called a spectral imager, which means that you have a spectrum at every pixel. So instead of just making a map, at every pixel you have a spectrum. So it's a 3D cube of data. You get the coordinates on the sky, and you also have a spectrum at each pixel on the sky. In optical, people call it hyperspectral imaging. I kind of like that. We should switch. Instead of saying we're building a correlator, I think we should say we're building a hyperspectral imager. It sounds cool. So beamformers we usually build if we have just a small number of beams. Correlators we build, they make an image of the whole field of view. So you get lots and lots of pixels, thousands or millions of pixels on the sky. Correlators are made of spectrometers, and I'll talk a little bit about that. I want to say a little bit about how arrays work, and we already heard from Dan about this. This is a slightly different sort of graphical interpretation. So if you have a single dish, it brings things to a focus. You can think of the single dish. Oh, you can see stuff off axis too. You can think of a dish is made of a bunch of panels, and you can break the dish, and now we have a bunch of panels here. But now I can do a trick where I can, instead of thinking of them as panels, I can think of them as individual telescopes along this imaginary parabolic shape. I can also, I can sum them up now, and I can get a focus. Now it's still equivalent to kind of a single dish. Or I can digitize it and sum it here, or I can put them all on the Earth here, on this flat surface, and I can make them into a parabola with these delays. So the light here hits this thing before it hits this thing. It takes longer to get here, but I can put this delay in there. I can make a digital delay, or I can make it just a long cable, and I can sum them up, and I can make this flat thing into a parabola with these long, different length cables. Then I can sum them up. Does that make sense? So this is a sort of graphical thing. So this is forming one beam. This is what I just showed you with different delays. But if you change the delays, you can look in a different direction. So here I've changed the cable lengths, and now I'm sensitive to a different direction. So I think Dan showed a similar thing. And you can make these delays digitally, or you can make them in analog. The old way was to make them out of different length cables and have switches that switch in different lengths. So a correlator is a way to make lots of pixels. So instead of just 2 of these beams that I showed you, you can look at lots of beams at once. And the correlator is the hardest thing that we build in CASPER. And if you're a new person to CASPER, don't worry about correlators. There is a tutorial about correlators. You can build a 4-input correlator if you want. Traditionally, correlators have been hard to build. You'd have to digitize the data at each antenna, and then typically you make a spectrum with an FFT. If you want, you can make a polyphase thing. And then you cross-correlate the data, where you multiply every antenna by every other antenna. So you have to, if you have 3 antennas, you have to multiply A and B, you have to multiply A and C, and you have to multiply B and C. You have to multiply all the pairs of antennas in your correlator. And traditionally, that's been a hard problem because of all this crisscrossing of data. So because you have to get all the pairs, you have data running every which way. And old correlators had millions of cables, sometimes this big around, running data all around to shuffle the data. That was the hardest problem in correlators. And we, in CASPER, we said, well, we need to rearrange the data like that, but it turns out you can buy something from industry that does that. So if you buy a switch, what's inside here, a switch can route any packet to any place. So this guy can send data here, he can send data to anywhere, this guy can send data anywhere he wants. And so we call it the packetized switch-based correlator, and it takes care of this interconnect problem. It solves a lot of problems. It actually doesn't, all we've done is we buy this thing off the shelf. If you look inside this switch, it's got a whole bunch of crisscrossing. It can send data. But industry knows how to build these things. They make chips. But it still has all that crisscrossing of all the data in it. It's just done for you. And so if this guy wants to send, what he does is he sends you know how Ethernet works. It's got a little address. Jason's going to talk about this tomorrow, right? Jason. So he sends a packet on Ethernet, and a packet has an address, and it says, I want you to send this packet here. Then he sends another guy a packet. He sends another packet out and says, I want you to send it here. And the switch looks at these addresses on each packet and figures out where to go. So it solves the interconnect problem. It's a nice way to build a correlator. It's a nice way to build all kinds of instruments. And a lot of new telescopes are called Ethernet telescopes. The Meerkat telescope is a great example. And I hope we'll hear about that. So CASPER is a collaboration of, I think, about 1,000 people, and I've only listed some of them here. I apologize if your name's not on here. Here's a map of some of them. I want to talk a little bit about the kind of science that's come out of CASPER. It's not coming out of my group, but I think you know that the first image of a black hole used CASPER. I think somebody mentioned, I think Jonathan mentioned, every byte that came out of a radio telescope to make this image went through a CASPER FPGA board developed in South Africa. Most fast radio bursts are coming out of CASPER-based instrumentation. Most pulsars are coming out of, this is the most massive pulsar ever found that came from one of our grad students, Paul Demarest. Found this thing recently, not recently, but it was the most cited paper in physics because they were interested in these very high density equations of state. The pulsars are really interesting. They make they're the best clocks on Earth, or they're not on Earth, but they're the best clocks in the universe as far as we know. They're better than atomic clocks or anything you can build on long time scales. And because they make such good clocks, you can measure all kinds of things. A couple of Nobel Prizes come out of this where if the pulsar moves a little bit closer to you, the pulses arrive a little sooner if it moves away, so you can measure gravitational waves. It's a really exciting thing to get these precise arrival times of pulses. Matthew Bales used a bunch of CASPER stuff to find a planet made out of solid diamond. It's used, there is a tool flow in CASPER, there used to be, where you can, instead of making stuff for an FPGA, you can make an ASIC. We don't recommend that. It's used outside of radio astronomy in neutron imaging, measuring strains, magnetic field imaging, crystal growth. So we used it a little bit in medical stuff to get, We used some CASPER hardware to get data out of a brain. We had electrodes in here. We use undergraduates for this. And we had 256 little electrodes measuring what was going on in your brain, and a radio link and CASPER technology to get the data out. We get about 40 megabits per second out of a guy's brain. And eventually we hope to use it for kind of you think and your arm moves prosthetic control, but we're not doing that yet. Okay, so the CASPER commandments. Should we do the repeat? Okay, thou shall not, not shall. I guess I wouldn't make a good priest. So you have to share. Okay, everything is open source, right? Please, if you make a little design, make a little piece of a library, you do what DP said, make it not n log n, but make it just n or log n, then you got to share, okay? So you got to help everybody, especially the new people, and you got to connect everything with Ethernet, and switches are free. So I think all of you figured this out by now, that it's an open source. The instruments are open, the libraries, the tools, reference designs. There's a lot of different. If you don't want to build your own correlator, you can probably down one or beamformer. We not just open source stuff for, we call it gateware, FPGA-ware, but we're starting to do more GPU-ware and software and sharing, and you'll learn a lot more about that as we go. We know, you know, that there are workshops. There are a lot of videos, and I believe there will be videos of this thing. Are we doing the videos of just the first 2 days, Jonathan, or I'm not sure?
I believe all the research presentations will be videotaped as well.
And there's a lot of good stuff on the website, and Jack can tell you about that. There's also a mailing list if you're not on the CASPER mailing list, where that's a really good place to get help. If you get weird error messages, you send that out, people will help you. And let's see, there's a lot of hardware that's not just open source, where the schematics are available, but there are vendors that make this hardware cheap, kind of a little bit more than the cost of the parts. The reason they can make it cheap is because we're all helping each other, so they don't have to support it. They build the boards, but you can't call them. You call one of us, or send something out to the mailing list. So the philosophy and the religion of CASPER, we're trying to make things quickly because of this exponential growth. You want to see if you can build your instrument in a few months or a year or something like that. We want to figure out how to do that. We think that you should think about getting in this mode where the signal processing the instrument is sort of part of the operating cost, that you should be throwing away your digital stuff every few years because it changes so rapidly. And I've got a few slides about that. This is radio telescope sensitivity improving as a function of time, doubling every 3.5 years. So when I started doing SETI, I built this thing with 100 channels, and I thought that was really amazing, 100 channels simultaneously. The guy before me, Frank Drake, had 1 channel. So I showed that to Frank, he was impressed. But now the new thing, this doesn't show, it's off the graph, is 100 billion channels. Not because I got smarter, it's just because this exponential growth. Correlators going up in a similar sort of way. This is computing power. Computers right now are as smart as a lizard or a guppy. They will be as smart as humans in 2030 or 2040. Very good if you're a radio astronomer, not so good if you're a human, but we'll see. But so this is a slide that shows the cost of an array of dishes. For you have a fixed area, how much does it cost? Should you build it out of little dishes, 6-meter diameter dishes, or should you build it out of big dishes, 25-meter dishes? And what you see is if you make them out of little tiny dishes, it's getting very expensive because of the electronics cost, the correlator, the computing cost. It goes as the square of the number of dishes. If you build it out of big dishes, the cost is dominated by the steel. What's interesting about this, there's sort of a cost minimum. It's kind of wavelength dependent. But the cost minimum is shifting down. Why? Because the electronics, this orange thing and the brown thing, is getting cheaper and cheaper exponentially. The cost of steel does not change. It's always the same price as hamburger. It's, you know, whatever the cost of steel is per pound, that's the same price as hamburger per pound. It's pretty level. But so what's going to happen is as electronics, the number of dishes will grow because electronics comes down, and they'll be made out of dishes. Arrays will be made out of smaller and smaller elements, so already we're seeing arrays with hundreds or even thousands of elements. So you should, think about what's going to happen in just the near future. We're going to have dishes with 100 gigahertz bandwidth, with thousands to millions of antennas, maybe up to 1 million beams, and very wideband receivers, low system temperature phase array feeds. So I think the future is looking good for radio astronomy. Some of the CASPER applications. Jonathan, our host, is an expert on this VLBI. That's what they did for the black hole image beamforming, a lot of SETI spectrometers. A lot of people are building correlators and imagers and beamformers. A lot of applications in pulsar timing and searching and various kinds of spectroscopy. The goal is to build, how am I doing, Jonathan?
You have 10 more minutes.
Okay.
10, actually 12.
The goal is to figure out how to build scalable and upgradable instruments that are sort of flexible and that you can upgrade. And some people are working on these fault-tolerant instruments, so if something breaks, it only takes out a little piece of the telescope or nothing at all. I mentioned some of these. You want to build instruments quickly in this exponential growth phase. You want to figure out how to build them quickly, open source, modular, upgradable hardware. Use Ethernet to connect everything. We think that's a good thing because Ethernet's been around for a long time. It's likely to stick around. One of the things that CASPER and other people developed is this idea that you could have multiple instruments on a telescope running simultaneously. This is a particular picture of what we're doing at the FAST telescope, but a lot of people do this where you have, at the FAST telescope, we're doing a big sky survey that takes 3 years. Instead of just doing one science, we have these instruments on it so while we're surveying the sky, we look for pulsars, we look for fast radio bursts, we have another thing that's looking at hydrogen, extragalactic hydrogen. We have all these different instruments, a SETI instrument running, I think, so we don't have to survey the sky 5 times, we all do it together. And some people split the signal from the receiver with analog signal splitters, but what Meerkat and other telescopes are doing now is digital data splitting. So you use the switch to split the data, and you can keep adding more and more back ends as you get wealthier, you can add more stuff. And Jason's going to talk tomorrow about these multicast switches that can provide data, and you can bring in an instrument and plug it in and add new things and grow the observatory. So the kind of general purpose architecture that most CASPER people use, they have a bank of telescopes. It doesn't have to be a bank, it could be 1 or 2. Then you digitize the data, and then typically you do spectroscopy. You might have a polyphase filter bank on every antenna, and then you put that data into a big switch. And then on the back of the switch, you have these different things that do different, they might do pulsar timing, or they might search for FRBs, maybe some beamformers, a correlator to make spectral images, put some computers, some GPUs, and this kind of dynamic environment, the astronomers can reprogram it to do whatever they want. You can have kind of dynamic allocation of resources depending on what the astronomers want to do that day or whatever. And if you have enough computing resources, you can do a whole bunch of things at once on this data. And some examples of that. This is a kind of another example of a correlator. I think Jason's going to talk about this, where you have these things called F engines, which are spectrometers, and then a switch, and these X engines, which are the cross correlators that are doing the multipliers with a switch in the middle. I mentioned that CASPER, we want to use Ethernet. We used to use 10 gigabit Ethernet, then 40, and the new thing that people are working on that you'll hear about is this 100 gigabit Ethernet, but it's Ethernet. And we think we like to use Ethernet because it's likely to stay around. It started in the 70s, but if you want to build an instrument that's going to last a while, you want to be able to plug things in and upgrade it, then we think Ethernet is better than these backplanes. Used to plug boards into backplanes, but if you're depending on your age, you might know some of these backplanes, but they're always changing out from under you. There's no they only last a couple of years, and there's something new. So you buy a board that plugs into a backplane, and then a few years later, you can't buy any computers that the board plugs into. But Ethernet, we think, is going to be around. And there's different ways you can connect. There's copper cables. There's a lot of optical interconnect. There's lots of. It's very cheap to connect stuff with Ethernet, and the switches are fairly cheap. And Jack's going to talk about hardware right after me. This is the Roach 2 board with, these are ADCs. This is an FPGA board. These are Ethernet connectors. This is a board that is a snap board, an FPGA, and it's got some ADCs on it. There's up to 12 signals that you can digitize, an Ethernet connector. This is Snap 2, which was developed in China. And these 40 gigabit Ethernet boards, so a lot of I/O. It turns out in radio astronomy, a lot of times you're not limited by how much computation you can do. You're limited by just moving all the data around. Sometimes you have terabits per data. So you find a lot of these boards have a lot of Ethernet ports on them. And there's a lot of ADC boards. And this is an example of one that I think this is a 16 input board. And one of the big things is not about hardware. We used to build a lot of hardware in CASPER, but now there are a lot of companies that are putting Ethernet on their boards. And so we're moving away from building our own FPGA boards and even our ADC boards. But a lot of CASPER work is in going to develop libraries and tools to make it easy to build instruments. And we want to make it sort of platform independent. So if you compile a design for one board and then you say, I want to upgrade to this next board, you don't have to make a lot of changes. So we use this language called simulink, which I mentioned before. It's this graphical thing. And if you're interested in it, there will be tutorials on Wednesday, Thursday, Friday, where you can, I think there's about 6 or 7 tutorials where you can learn how to program these FPGAs. So an example is if you plunk down the FFT block, or the polyphase block. If you plunk down the FFT block, it'll say how many channels do you want, what bandwidth do you want to process, do you want complex or real inputs, how many polarizations do you want. So all these blocks are kind of parameterized to build whatever kind of spectrometer you want to build or whatever kind of correlator you want to build. There's another thing that CASPER does where you want to you might start with your data in FPGA, but you want to get it into a CPU or a GPU. And it turns out that it's not just a matter of connecting one to the other with a cable. It turns out to get high-speed data into a computer or a GPU is a lot of work. If you just use the regular kind of software, it's not very good at moving very high-speed data. So there's a tool that Dave McMahon, Dave, are you around here, developed called HashPipe. He's up there. And HashPipe is very high-speed data transfer. You can do up to 40 gigabits per second and get it into a CPU or a GPU. It's a nice set of little modules. And there's a tutorial now that I think Pei Shin developed about how to use HashPipe. So there are tutorials. I'm not sure if this is the current list, but how to use 10 gigabit or 40 gigabit Ethernet. There's something about that introduces you to Simulink. You can build a spectrometer, correlator, and these are things that you can choose to do. There's this HashPipe thing where you can learn about high-speed data transfer. And these are things that you'll be able to do on Wednesday, Thursday, or Friday. Thanks very much.